area of a triangle is half times the product of its base and its height. Yep, we're back in your typical high school geometry class, and the teacher's presenting this problem on a board along with possibly a picture. But wait a second, how did we get to that formula? The teacher might present a bit of a proof for the formula, but then that only raises more questions. How do we come up with that proof? So we never really get an answer to those kinds of questions, and so we're left wondering what's all these weird questions about what the point of this is and how do we come up with it. And math is basically reduced to just a set of formulas and algorithms that we're just supposed to know. So this isn't exactly optimal, but we could try to just doodle around with this picture, and maybe we might draw a line down the middle, just for fun. There's no real purpose in it. The triangle doesn't really represent anything here. I'm not trying to make any useful purpose out of this picture, but when we do that, we see that we might divide the picture into two parts, where each diagonal line divides a rectangle into two equal parts. And so that way, since you know that the area of the rectangle is the base times the height, the area of the triangle is half times the base and the height. And so the formula makes a little more sense now. But again, we didn't have that much of a use for it right now. So this example, as it was presented by Paul Lockhart in his paper, A Mathematician's Lament, shows us that there are really two different ways to teach mathematics. One, where it's just for the sake of itself, the second one, and the first one where it's applied to science, engineering, and economics, subjects like that. So, both of these are really useful, as you can see. The first one has applications into the various subjects, and we really get an understanding of how it's used. In the second one, we really just enjoy it more, and we can kind of get a deeper insight into where the mathematics comes from. Now, so we see that this is more useful but less stimulating, and this is more stimulating but less useful. Now I'm going to term these as math as a tool for science and math as an inherent art. So we see that there are two different kinds of mathematics, and they're both very separate. Now what we really want is to find a way to combine them, to make them into inherent whole. So that's what we're looking for, the intersection of this Venn diagram. Now, this can seem very difficult. Like, in an interview with Yuri Boriku, a mathematician at Stanford University, he's described that his mathematics experience was more on the side of teaching math, where it was taught as a tool for science, but he had to search for material outside of the school to get to the latter side as an inherent art. So Yuri Boriku is a professor, or not a professor, a teaching assistant here, and he competed at many international competitions in creative mathematics, which is the blue side of the picture. So he definitely has exposure into both sides, but he claims that it's still very difficult to get to a sort of a middle between the two. He says that most teachers can't actually do that, and it's not possible to get the two together. So from that vein, you see that it's more effective to actually split them up into two parts. So instead of having it as a tool for science and as an art, it should just basically be more like this, where they're two separate pictures and they're both taught separately. Now, this sort of a framework for a curriculum might seem very radical, and so you might wonder why should it even be used or considered. The issue with this is that it's actually quite elegant in that it splits it up to what we have before and adds something to help the people that actually want to do it, who can get bored of the scientific math and search for something more stimulating. Now, a system for this has actually already been in place, or an attempt to solve this problem has been already in place in many countries, such as the United Kingdom and at some graduate programs in mathematics, such as at MIT. So this system is for dividing math into pure math and applied math. So this attempts to model the same kind of distinction that we talked about before, where we have math as a tool for science and as an art. Pure math attempts to model the math as an art, where you try to just go into math and focus on the more intangible aspects, while applied math focuses on the more tangible aspects. So, in applied math, you have ideas such as graphs and tables and more applications towards mathematics in the subject we talked about, like economics, science, and engineering. pure math, you'd have more ideas in algebra, combinatorics, and basically more theoretical mathematics. Now this system has been implemented and actually has been received with a lot of success. It was implemented more around the 1950s in the United Kingdom, as since then, like, percolated into most of the countries that were once ruled by the United Kingdom. And so it has been received with a lot of success, but it doesn't exactly conform to the ideas that it actually intends to solve. This system actually doesn't the pure mathematics actually isn't purely the ideas of math, and it actually is aimed with the intention of teaching the applications, except with a more theoretical perspective. And the applied mathematics focuses only on the application and doesn't actually represent the ideas of the pure mathematics at all. So, while this system is good, it doesn't actually solve the problems. So, in conclusion, I'd like to just go through the 3 points that I've been going through. One, that there are 2 ways to teach mathematics, and it's not best to try to combine them into an inherent whole, but to split them up. And thirdly, the system of applied math and pure math is good, but it's not perfect, and it's lacking in certain aspects. Thanks a lot.